All right, everyone. So welcome back to CPAC 458 malware analysis. And today is going to be a very hands-on class where we look at various examples of how to do reverse engineering in IDAPro. In the last class, we talked about what IDAPro is and what it does. Basically, IDAPro is a very invaluable tool in advanced static analysis. And we talked about how to run IDAPro, and we talked about how to enable some of its nifty features like line prefixes, enabling comments, and things like that. I mean, I will quickly show how that works. So, and for today, you want to make sure that you get your VMs ready and get the files for this class ready. And we'll be doing a lot of hands-on, okay? And so we're going to start IDAPro. You can find it in your programs menu. Should be somewhere in here. So IDAPro free. So stack pointer display, sure, it doesn't hurt. And then you can go to, as I said on the slides, you can go to options, general, and line prefixes. I think you have to first open program. So the first thing which we're going to look at is if you open up the exercises for today's lecture, what we want to do is we want to take ProgiMath. It's a very simple program, and just drag it into IDAPro. You may get a bunch of questions. Basically, just answer affirmatively, yeah, overwrite, and then click OK. And keep clicking OK until you get something that looks like this. Now, also, some of the useful things that you should enable is you should go to Options General, and you should enable auto comments. You should enable line prefixes, and all of those are very useful things. All right. So this way, I'll be able to get more information. So let's jump right into it. So what you're seeing right here is basically the program. It's a very small program, a very simple program. And before before we go on, let's take a look at some of the really nice things that IDAPro provides for us. So in this window, which says names, it basically gives us the names of things like functions and other useful kinds of things. So like, for example, if I jump somewhere, let's say so when I click on _cexit, it'll go to the cexit function. Now, it's just a library call, so I'm not really that interested in it. But if you click on main, it'll bring me right back to my main program. So this is the disassembly of the main function. Also, another very useful thing which we can see right here is the strings window. Basically, the strings window does the same thing as the strings functionality, and it'll give me all of the strings that are in the program. Now, if you click right behind the window, you'll see a lot of other useful things. Like, for example, there is the function window. So let's take a look at that. What exactly is the functions window? So basically, the functions window contains the functions that are defined in this very program. And I can skip to them by clicking on them. All right? So that's basically the idea on this one. There is also a hex view. So hex view gives me what my program looks like in raw hexadecimal. All right? What it looks like in raw hexadecimal format. If I click right here, I get something similar to what I would normally see with the dependency walker. So I get to see the functions which are being imported into my program. And we've seen names before. So basically, names are names of things that are identified in my program. They are primarily functions. So the strings window. This one will be very useful as well. This is the structs window. So now, So if I want to go back to the main, I just go to functions and I click on main, and it'll take me right there, and I go to IDA view A. All right. Now, one thing to keep in mind, like even if I take a file and I write some random stuff into it, whenever I view it in IDA view A, IDAPro will try to parse the random data into instructions. However, just because you'll see some instructions does not mean that they're actually instructions. Okay. Now, because I'm dealing with an executable here, we are dealing with instructions. So, and yes, actually, you can, Carla is asking a question, can you write comments in IDAPro? And the answer is yes. You just right click and you choose enter comment, and you can enter a comment. For example, cats are cool, and boom, see? And if it's in blue, it's basically my comment. So folks, so here we are. So like I said, IDAPro allows us to do a lot of static analysis too. So like if I look right here, this is basically the same thing as the strings dump. And if I click on a string, it will actually take me to the part of memory where it is defined. And notice, it's in the R data section. When we talked about basic static analysis, remember how we talked about how the PE executable file is made up of different sections, and R data stores the read-only data, right? So this string is stored in the R data section. Let me stick with a hex view for a second. So if I scroll all the way up, you can see that it's showing me parts of the text section. So if you remember, text section, it stores the executable instructions. Then I have the data section, which stores the global variables and static information like the constants. Then I have the R data, which is the read-only data section. So it'll store basically the read-only data, which could also include constants. Then I got a .bss section, which could be used for other kinds of data. Then there is IDATA, which is the imports, etc. So basically everything which we talked about when we talked about the PE executable file can be found like we here. Like basically it's just showing me the file byte by byte. All right. So, oh, and here are the exports. So those are the functions which my program exports. They are the functions that are accessible by other programs. All right. So let's go back to main. So I'm going to click on functions and I'm going to click on main. All right. And then, let's see, I'm going to go back to IDA view. By the way, you can move around the map by doing this. Like I'm moving around this mini map and it'll navigate me around the map. So how do we do this? And if you want to do the comment, you just do edit comment, or yeah, I think you got to do enter comment and then you just do that. Okay. You delete it. Now, so how do we begin analyzing programs? Well, so we are in the main function. So everything which you see in front of you is the code for main. So what does it consist of? Well, I will give you a little hint. So basically, in all of the programs that we'll be working on in this class, if you see code which starts like this, basically starting from push EBP to the second call to procedure, this is compiler generated code. This code is used by the compiler in order to set up the stack for the main function. And then the real stuff, the actual program code, begins right after that. So basically, you can always skip everything from the beginning to the call to the second sub. So what exactly is going on here? Well, I see a move instruction which says move the value of 5 into the memory location referenced by EBP plus var4. Now, folks, whenever you see EBP register, this usually means that I'm accessing a local variable. Now, but if you remember, stack grows from higher addresses to lower addresses. So typically, all of my variable addresses will be EBP minus a value. So why is it a plus? Well, folks, it basically just has to do with IDAPro trying to make things easier for you. So if I click on var4 right here, it'll highlight every instance of var4. And as you can see, var4 is actually a quantity that is defined up at the top, and it represents a literal value of -4. So basically, var4 is -4. So really, what this is this is just EBP minus 4. In fact, you can sort of assume that whatever value you see right here, whenever it's for EBP, var4 would mean EBP minus 4. var8 would usually mean EBP minus 8, right? So that's basically the idea. So what am I doing over here? So it looks like I got some local variable located at the location EBP minus 4, and into that, I'm moving the value of 5. So if I was to translate this into a high-level program, okay, or into high-level logic, so I would have my int main, and I have some sort of a local variable. So what is that variable? Well, IDAPro called it var4, so I'll just call it var4. So basically, we are assigning a value of 5 to some variable, and then it looks like, what does this do? What do you think? Please help me. What do you think this move instruction does? This one, on which I have my mouse. Yeah, it moves the value of 6 right into some local variable located at the location of EBP minus 8. So basically, in my program, I got some variable. I'm going to call it var8, and into it, I'm copying the value of 6. All right. Now, and what am I doing next over here? So basically, next, it looks like right here, I'm copying the value of variable var8 into EAX register, right? So I have EAX is equal to whatever var8 is. So var8 is equal to 6. Okay, and you know what? I'll just get rid of main, and I'll just keep track of all of my variables. Okay, so EAX register is now equal to 6. Now, next, it looks like I'm executing an add instruction. And what does this instruction add? What are the two things that it's adding? Yeah, so it's adding EAX to variable 4, which means what? EAX is going to be equal to, right, whatever is in the EX right now, plus the value of variable, of which variable? Variable 4, right? And the value of variable 4 is 5. So it's equal to 11. What did we just effectively do? I mean, if I come back a little bit, doesn't it look like I have just added the values of variable 4 and variable 8, right? So because I set variable var4 to 5, variable 6 to 8, and then I stored the value of variable 8 in EAX, and then I added EAX to variable 4. This is logically equivalent to just adding variable 8 to variable 4. Now, what is happening next right here? What does this do? What does this do? Yeah, so it moves EAX into some local variable, var_c, and var_c is defined as -ch. So basically, it looks like we are copying the value of EAX into some new variable, which is var_c. And what is the value of EAX at this point? It's 11, right? So we're copying the value of 11 into variable C. Now, what happens next? Well, it looks like we're moving the variable EAX into this address. Now, folks, if you remember the ESP register, right, it always points to the top of the stack, right? So if this is my stack, right, and I get a bunch of stuff on my stack, ESP would always be pointing to the last thing on my stack. And remember, stack grows from higher addresses to lower addresses. In other words, it grows from up to down. So what am I doing here? Well, it looks like I'm adding 28 hexadecimal to var20. What's var20? So var20 is negative 20. Okay, so 20. So if I do, so I'm just using Python as a calculator. So if I do 28, right? 28 hexadecimal plus negative 20, which is basically the same thing as minus hexadecimal 20, I'm going to get a hexadecimal value of just 8, okay? Positive 8. So I'm doing ESP plus 8. Now, so when I do ESP plus 8, basically what I'm saying is I'm moving 4 bytes this way and then 4 bytes that way. So what do you think I'm accessing? So if you remember our lecture on the stack, you will recall that, and let me actually pull that up. One of the things on the stack that is above the local variables of the function, we have the old value of EBP, and there is return address, and then there is the parameter space. Okay? So what exactly is going on right here? So when I'm doing ESP plus, basically it looks like I'm moving the values into the parameter space of the new function that I'm about to call. And folks, whenever you see something like this, right, ESP plus that, basically, typically what we mean is chances are we are getting ready to call a function. And one way to sort of convince yourself of that, just skip a few lines down and you'll see that after a bunch of statements like this, okay, you will see that we end up calling some sort of a function. So, and indeed, I'm calling a function right here called fprintf. And what exactly is fprintf? Well, if you don't know, we always do research, okay? So, and there's going to be a lot of things that you don't know in the process and you'll have to research them. That's just the way in which malware analysis works. So, yeah, basically it prints stuff to a specified stream. So basically the way in which it works is the first parameter is the stream where you want to print things. Now, a stream could be a file pointer, in which case the data is going to be printed into the file. It could be std out or std error, which would print it onto the screen, either into the standard output or the error output. Next, you have something called the format string, which specifies how you want to print your data. Do you want to print integers? Do you want to print strings, etc.? And then finally, the variables that you want to print. However, typically, whenever we add arguments to the stack to call the next function, we always add them in a right to left order. So let's go ahead to IDAPro and let's see what is going on here. So it looks like I'm copying the value of variable C into EAX. Then I'm copying the value of EAX into a place on the stack at offset of +8. So then it looks like when you see offset and then a name, it typically means I'm copying the address of a certain variable somewhere. And in this case, once again, I'm copying it into the variable space. Now, what exactly is this thing? Well, I can always find out by clicking on it, and it'll tell me what it is. Okay, it'll tell me its value. All right. So when I look at it, I can see that it consists of the byte called 25H and then another byte which says 64H. Okay, and then another byte which 10H. So now, and IDAPro has been nice enough to me to figure out that this represents a percent and this represents character D. So basically it looks like what I'm trying to call, or in the process of trying to call, is, so remember, so we have function fprintf, right? And we're moving the variables in reverse order. So basically over here, I have my variable that I'm passing var c, and then it looks like right here, I have a string %d, and then remember that OH, well, that basically means new line. And once again, IDAPro has been nice enough to do that, to identify those characters for me. And what's happening next, right after that? Well, it looks like I'm moving into the EAX, the value in ds::IOB. Okay, what in the world is that? Well, folks, whenever you see ds::, this means that the variable which we're accessing, it's not a local variable, but it's in the data section. ds stands for data section. To be more specific, ds is the starting address of the data section, and then :IOB basically means that I want to access something in data section at offset of IOB. Okay, so into the EAX register, I'm copying the value of some global variable at this offset. The next thing that I'm doing is it looks like I'm adding a 40 to the value of that variable, and then I'm copying that variable into the parameter space of the function. Now, folks, what exactly does this do? Well, since I know we're calling nfprintf function, right? We know that, well, we also know that it's finishing off the last parameter because it was the last thing moved in, and we typically do it from right to left. And we have already taken care of the rightmost variable and then the formatting string. So this represents the stream. So, and through experience, whenever you see code like this, you will know that it is basically another way of saying that the stream is std error. And this is something which you would find out by research. But, you can basically steal this experience right there. Okay, it's just the way in which we specify std error. Now, and what do we do next? Well, we call function fprintf. So basically, we just called function fprintf with those parameters. And what have we got here? Well, basically what we're saying is we want to print into the error stream the integer value variable c. So basically, in this formatting string, %d will be replaced whatever is the value of c and end line. All right. And what happens? So basically, we're printing out the value of variable c. And what happens next? Well, it looks like right after that we're moving EAX into something like this. Now, folks, once again, whenever you see something like this probably means what? What are we getting ready to do? Help me. Yeah, we're getting ready to call a function. And once again, whenever I see something like this, the first thing I do is I skip down a few lines, and then I look at the function call. Oh, look, it looks like, right after this, we are calling function called system. So what exactly is the system function? Well, basically, that's where, you would say, well, I don't know what it is, and you basically would Google it. So you can do C system function, and you would see that this function is basically used to run commands. Okay, so like, for example, I can do something like this. So if I do system pause, it'll run the pause command in the terminal. Okay, so it's as if my program has ran the pause command in the terminal, which will basically, as the name implies, will cause the program to pause. And I can run any command, basically. I can do dir, which will run the dir command, and it will, we will get basically the list of directories printed. All right, and yes, on the exam, you will be allowed to do this kind of research, because, I mean, it's just part of malware analysis. Okay, so now let's go back to IDAPro. So basically, it looks like we are copying the address of something into the parameter space of the system function before we call it. Now, look at how nice IDA is to us. It even is telling us the value of the thing whose address we're copying into the parameter space of system. It says that it's a string called pause. So, okay, so we're copying the string pause into the parameter space of the system function, and then we are calling the system function. So we can conclude, right, that we're calling system with the pause string. All right? And what happens next? Well, folks, what happens next is that this code is basically return 0. Okay, that's how return 0 is implemented in a function. So as we will talk about today, one way for a function to return a value is inside the register. So before the function finishes, it'll move the return value into EAX register, and then the caller will simply examine the value of the EAX register. Then you have the leave instruction, which will restore the EBP register, and ret n will basically transfer execution to the compiler-generated code that has invoked the main function, and then that code will take care of properly terminating the program. All right, so we have dug very deeply into a lot of details, but let's sort of pan out, because remember, never lose sight of what's important. So what does this program do? So can you please help me on this one? So what does this program do overall? Like, what is it going to do? All right, help me. Okay, it adds two numbers, right? And it prints the sum, right? And then it pauses, right? Yeah, and yeah, yep. And Carla is right, and Lauren is right as well. All right, so now let's look at the source code which I provided of the ProgUmath. And let's see what it's actually like. And there it is, right? So let me scroll up so we can relate it. So basically, what we got is, so we have variable a, and we copy the value of 5 into variable a, so our 4 represents variable a. Then we copy the value of 6 into variable b, so our 8 represents variable b. And by the way, folks, did you know that IDAPro allows you to rename things? So just to make it easier, I can click on a variable and I can click rename and I can call it a. And then I can take this and I can rename it, and I can call it B. How cool is that? Okay. So yeah, and then Lauren is asking on the exam, if we're giving this, would we tell you what we think the program does based on the assembly in IDAPro? Oh yes, definitely. There will definitely be questions like that. Yeah, absolutely. Yeah, that's one of the biggest things in malware analysis. So now, and then what do I do next? It looks like I add the two values. So I add the values of A and B, and this is being achieved by by those two lines, right? So basically, I add the value of A to the EAX, which at this point contains the value of B, and then I copy EAX into var C. So it looks like var C represents, we're kind of lucky, well, variable C. And once again, I can right click on it and I can always rename it. Okay. Oh, one more thing. IDA is also super nice to us in another way. When I right click on C, it will actually also gives me a list of the actual values of those local variables. How cool is that? All right. So, and then what happens is we're calling fprintf, and we're printing out the value of C. So basically, that's being achieved by this, and that line, and then that line. And you thought that calling a function is a trivial thing. Then next, we're calling system pause. So basically this one. So we're copying the address of the string pause into the parameter space of the system function. Then we're calling the system function. And then the only thing left is return 0. So the main function will return the return value of its code into the EAX register, which will then be examined by the compiler generated code that invokes main. Does that make sense, folks? Do we have any questions? Not so bad, right? Right?
Professor, I had a question. So I was trying to follow along with your code on my end, but when I opened up Proggy Math, I got a different set of functions. So I wasn't sure where did I look in the wrong area for Proggy Math, or I followed the same as yours.
Yeah, so basically you would click on the functions tab like I'm doing right now, and then you click on main, and then you can navigate, and you should see something like this.
Okay, cool. I see it now. Okay. So I guess I was looking at the overall program, but I didn't find the correct subset of the program, like the jump to function or something.
Yep. Yep. No worries. Yep. All right. So, yeah. All right. Does this make sense, folks? Right? Not so bad, right? Do you see like how powerful it is? I mean, just let's just pan out a little bit. I just gave you a program. I didn't tell you a thing about it, and you were able to reverse engineer its logic. Do you see how powerful something like this is in malware analysis? Now, one of the skills which you will develop as a malware analyst as you work on this more and more is that you will be able to actually not just being able to figure out what certain parts of the code do, but also know what to ignore. Because real world malware, you dump it in and it'll be, well, oh, mamma mia, right? That's going to be the, the reaction. Oh, mamma mia, right? So I'm just a poor boy, nobody loves me. Okay, that's enough. So anyway, so you will know what to ignore. Yeah, that was a great song. Mother. So, and then also IDAPro will also show you the structure of the program. And oftentimes you'll be able to infer a lot. Yes, this is on exam 1. You will be able to see a lot of things just by looking at the structure. And that's the next thing which I would like to try. So I'm just going to close IDAPro. Now, I mean, I know it's not, the most elegant way of doing it, but I sort of prefer to do this way. It's just a habit. All right, so I'm going to restart IDAPro. And the next exercise that I want to look at is proggy if. Okay, so let's go ahead and let's drag in proggy if. And yes, this is definitely within the scope of the first exam. Okay, and we've gone through it during the review session as well. So now, folks, so what is this exactly? Yes, we do have the source code, and we'll look at it momentarily. But look at what's going on. Well, as I told you before, that this is just the code which we can ignore. This is just setting up of the stack. But if I look at the map over here, this one doesn't look the way that the other program looked, right? There is a split. And whenever you see a split like this is IDAPro telling you that you have a conditional branch. So the green arrow tells you what's going to happen if the branch is taken, and the red arrow tells you what code is going to be executed if the branch is not taken. And the blue arrow basically tells you the branch that is unconditional. Basically, that branch will always be taken. Now, folks, let's say that I'm curious about this branch. So, what I'm doing here is it looks like I'm comparing the value of EAX against the hexadecimal value of OAH, which in base 10, it's, 10, right? And as Joseph points out, it looks like I'm comparing the value of EAX to 10, and then I have a branch, jump if less than or equal to. So if the value of EAX is less than or equal to 10, I'm going to execute this code. Otherwise, I'm going to execute that code. All right? And then it looks like after that, what does this code look like again to you? Help me. Help. I need somebody. Help. Not just anybody. All right? Okay, I guess one way in which I can get people to do things is I'll sing, because my singing isn't pretty. I know that. I used to have actually a pretty good voice, but as I got older, it broke down. Okay, so now, so basically, yeah, I'm returning 0, right? So basically, whatever jump I take, I end up returning 0. So let's take a look at what this program actually does. So like I said, we can skip all of this code, right? It's just setting up the stack. And what's going on right here? What am I doing? So it looks like as, so what does this do?
You're going to create.
What does it look like? Go ahead. Mm-hmm.
Creating a local variable?
Yep, it's creating a local variable, right? And it's moving the value of 1 into it, right? So I got some local variable. Let's call it var4 because that's what IDA called it. And it looks like I'm setting it equal to 1, right? And what about the next one? What does this do? The line right after.
Creating another way called.
Yeah, it's copying. Yeah, it's copying the value of 2 into another local variable. By the way, be careful when you say that it's creating variable 8 and variable 4. It actually doesn't create them right here. If you remember from the stack lecture, right, the local variable space is actually, it's happening right here, right? So remember, we back up the EBP register, which points to the base of the previous frame, and then we make EBP point to the base of the current frame. And you see this where we're subtracting hexadecimal 18H from ESP. Basically, what we're doing is we're moving the ESP register down. So that's where we're allocating the space for local variables. Okay, so the actual allocation of memory for local variables happens right here. And then right here, we're just setting that memory. Okay, so be careful when you say create. Okay, so basically, as you pointed out, what's happening right here, right? We're moving the value of 2 into some variable, and I'm going to refer to it as variable 8. And what happens next right here? Can somebody help me with the next 2 lines? what's happening right here?
We're moving variable 8 to EAX, and then we're going to add variable 4 to EAX, and we use EAX because that's the standard for add.
Yeah. So basically, the first line is going to copy the value of variable a into EAX, right? So basically, EAX is going to be 2, right? And then I have the add function, which adds the value of variable 4 to what's already in EAX. So the value of our 4 is 1. So basically, what am I doing? I'm basically doing 2 plus 1, right? It adds them together, right? As Lauren points out and Carla points out, right? So now the value is 3, right? So basically, EAX is now equal to 3. Now we come upon the next instruction. So we have already talked about this. So what does this do? Yeah, it compares it to 10, right? So yeah, basically it compares the value of EAX to 10, as Joseph and Lauren point out. And then what's going to happen is, so if EAX is less than or equal to 10, it will take the green arrow, okay? Basically, that's what happens if the jump is taking. And if EX is not greater than 10, then it'll go to the red arrow, okay? Means non-taking. Make sense? So what does it look like it is trying to do? So to me, it looks like it's doing if EAX, right, is less than or equal to 10, right? Right? And Joseph is asking, so does green represent true and red false? Exactly. Yep, you got it. Yep. So basically, if EAX is less than or equal to 10, basically here we have green. Otherwise, we have red. Okay? Does that make sense? Yeah. So now, let's take a look at those green and reds. And by the way, folks, in this program, do we know what it's which jump it'll actually take when we run it in this specific program? Okay, Lauren says no, and Carl says yes. Okay, so who's right? And Albert says yes. All right. So who's right? Well, the question is, so why do you think it is what it is? And Ryan says it goes to location 401 today. Okay. So what made you arrive at your conclusions? Well, so Lauren says, wait, since green should be yes. Yeah, green should be yes. Yes, and Carla is absolutely correct, right? Because in this program, right, the values of the two variables are sort of hard-coded, and whenever we do this comparison, EAX will be 3, right? And we know that 10, so EAX is less than or equal to 10, right? Because 3 is less than or equal to 10. Most of the time, right? Make sense? So we know that it'll go towards the green, right? Yeah. Well, so Lauren's asking, in most cases, it'll be hard-coded. Well, I'm not saying that in most cases it'll be hard-coded. I'm saying that in this case it is hard-coded. In practice, it will not always be hard-coded because, for example, let's say that the values of those variables, they depend on things like user input or data received from the network. So, and that's where static analysis cannot really tell us what exactly is going to happen once we run it. It'll tell us what could happen, but it won't tell us what will happen. Okay, that's why we also need advanced dynamic analysis. All right, but in this case, it is hard-coded, so this program will be deterministic. Does that make sense, Lauren? So now, let's take a look. So what's going on in the green case and in the red case? So let's first take a look at the green. Okay, so we have LEA var 8 into EAX. Ooh, the good old LEA instruction. What does LEA do? So LEA stands for load effective address. So basically I'm saying that I want to copy, as Albert says, I want to copy the address of EBP plus var8 into EAX. So in other words, EAX is now equal to the address of variable 8. So in other words, it's sort of like I'm storing the pointer to variable 8 in the EAX register. Okay? And what does the next instruction do? Well, what does EAX store at this point? It stores the memory address of variable 8, right? That's what I have accomplished by this line right here, right? And so, and then what am I doing right here? I'm doing inc double word pointer. So in other words, I'm saying that take the memory location inside the brackets and increment the 32-bit value that is stored in that memory location by 1. So what is it doing effectively? What is the ultimate meaning of those two lines? Yeah, it's incrementing the value, right, by 1. It's a plus plus. And what is it plus plussing? Which variable? Variable 8, right? Because right here, we loaded the address of variable A into EAX, right? And then we incremented the memory that stores variable 8 by 1. So really, folks, it seems like, the green part just says var 8 plus plus. Okay? Make sense? No worries, no worries. Making mistakes is part of learning, right? And now let's take a look at the red side. So what happens in the red side? Oh, look, I have another LEA instruction. So what does this LEA instruction do? What do you think it does? Help me? Yep, it gets a pointer to variable 4, right? It gets the memory address to variable 4, and it stores that into the EAX register. So basically, right? So what I have here, I have EAX equals variable 4. Yeah. And some of you have already figured out what it does, right? Because the next line, it says increment the contents of the memory address stored in EAX by 1. So basically, it looks like it's doing var4 plus plus, right? So var4 plus plus, all right? So, and then after that, regardless, and then after that, we have an unconditional jump, which jumps to this code right here. And what does this do? Again, I think Aiden has pointed out before. It does return 0, right? So basically, it looks like what we have is, so let's summarize what this code actually does. So, all right, so Joseph says, is sum of variable 4 and 8, if it's greater than 10, we're doing var 8 plus plus, or otherwise we're doing var 4 plus plus. All right, so now let's take a look at the source code and see if we're right. So this is the actual source code. And yes, folks, you nailed it again. Okay, so basically we got, two variables. I set variable A to 1, variable B to 2. I add them together and I check, is A plus B greater than 10? And if that's the case, I increment A plus 1. Otherwise, I increment B plus 1. I increment B by 1, and then I got a return value, right? Is this beginning to make more sense? Right? Yeah, awesome. And I think Joseph has raised his hand. Yep, go ahead, Joseph.
I had a question. So the A plus B portion, could we make an assumption that it's within the if statement due to the fact that we don't actually save the value returned by A plus B?
Yeah, we could. Yeah, we could. Yeah, we can definitely do that. Yeah, and also notice, right, how here I have A plus B greater than 10, and the compiler has turned that into a JLE, right? But the logic is the same, right? JLE means, jump if EX is less than or equal to 10. So it's sort of like reversed it, but the logic is still the same. All right. And Albert's asking, why does the else section have a jump instruction but not the if section? Well, there is actually a good reason for that, because you see, right now we're in the flowchart view, and if I look at the linear view, so if I right click and I go to text view, this is what the program actually looks like. Okay, so it's kind of linear. So basically over here I have, so I compare the value of x against 10, and if the branch is taken, I'm going to jump to this location right here. So I'm going to jump to that code right there. But what happens if it's not equal? Well, if it's not equal, then the JLE will be skipped, and I will go basically right into the else, and I'll do increment. Now, if this jump wasn't here, it would then go down and also execute this if code. But I don't want to execute this if code if I went into the else. So basically, this jump code sort of like jumps over that code, if you know what I mean, and goes right into the return 0. Make sense? Yeah, basically, you see, because we were in the chart view. And graph view is amazing, folks, because you see, so I just open up this program and I haven't yet looked at a single instruction, but look, when I see something like this, what is the first switch which goes off in my mind? What happens? It tells me, right, we got some kind of a jump, right? Some kind of a decision that is being made, right? Make sense? Yeah, a conditional, right? Right? Yeah, branches everywhere, right? Does that make sense? All right. Carla, Joseph, Lauren, Albert, Schmiket. Okay, Schmiket gets it. Yeah, actually, I think Schmiket probably, he has attended probably more lectures than most students. Yeah, right. So don't tell him the answers like during the exam. Okay. All right. Sometimes, when I look in his eyes, it seems like he's trying to say something. So yeah, so just ignore him. All right. So now, the next question, maybe he is, right? The next question, which I'd like to take a look at, is an example of something else. Now, so I'm going to reload IDAPro, and I'm going to open up Proggy. So, and I'm going to close Proggy if, and there is another program right here called Proggy loop. All right, he's trying to communicate the answers, right? So what I'm going to do next is I'm going to open IDA again, and I'm going to drag Proggy loop into the program, into IDA. And just answer, just agree with everything IDA says. She knows what she's doing. And now, so I haven't yet looked at a single instruction yet, but what do I already know? Like, what's going on in this program? I haven't yet looked at a single instruction, right? Haven't looked at a single instruction yet. Yeah, so it looks like we got some kind of a branch, right? We got some sort of branching going on here, right? Now, what, so, yep, go ahead. Mm-hmm.
How could we put it back into image, like a graphical view again?
Oh, yeah, so right now I'm in the graphical view. So when you're in the text view like this, right, you just right click on it and you go to graph view like this.
Thank you so much.
Yep, sure. Yeah, so basically here is what we got. So we got some kind of a branch. Now, let's take a look at some things that we can recognize. Now, do you see this green arrow, right? That's what's going to happen when the branch is taken. Yeah. So basically, what does this do? Doesn't this code look familiar? This compiler has very little imagination. Yeah, basically, it's return, right? It's a return value. So basically, it looks like the main function is returning. So now, let's go ahead and let's analyze it. Oh, by the way, look at this. Looks like there is a string, and we're calling a printf function after moving a string into the parameter space. So, okay, so looks like this program might be printing, I'm a little proggy. Do you see how we haven't really analyzed anything yet, but just by looking at it, how many things we've seen? Oh, and also Danny points out another good thing is that, so looks like if this branch isn't taken, right, then this code is going to be executed, and then we have a blue arrow from here to the beginning of the branch. What does this blue arrow mean? Probably means we have an unconditional jump, right? And folks, as we do more of this, you know, you will immediately learn to see you got a looping situation happening here. So let's go ahead and let's try to analyze it. What's happening here? Now, like I said before, this is compiler generated code, so all of that we can just ignore. And it looks like, what are we doing right here? Looks like we're copying the value of 0, right, into a local variable, which is variable 4. So basically, we got var4 is equal to 0. Now, please help me with what's happening right here. What am I doing here? What does this do? Yeah, it's a comparison, right? So it is comparing the value of variable 4 to 9. And then, if variable 4 is greater than 9, then basically we end up going the green route. So it looks like we're basically just exiting the loop, right? Because, and the reason I know we're exiting the loop because once we go here, we have the return code and there is nothing after that. By the way, another dead giveaway is main end p. As you may remember from 240, that basically means that's the end of that function, right? But, so, however, if variable 4 is not greater than 9, in other words, if variable 4 is less than or equal to 9, right? So then we're going to go to the red route, right? So what's happening right here? Well, it looks like I'm copying the address of a string, I'm little proggy, into the parameter space of the printf function. And then it looks like I'm calling the printf function. So what will this do? Yeah, it'll probably print, right? I am a little proggy. Yeah. End line, right? So, and then, yeah, so I think Joseph got it, and Alex is getting it as well. So, and what happens right here? Yeah, we're in, so yeah, and some of you are already picking up on this, right? So basically we're copying the address of variable 4 into EAX, and then we're incrementing the contents of memory pointed to by the EAX. So basically, essentially, we're incrementing variable 4, right? So, and then we have a jump instruction which goes to the beginning. So doesn't it look like we have a looping situation? So basically, it looks like we might have a loop which looks like this. So var4 is equal to 0, right? And while var4 is less than or equal to 9, we do var4 plus plus, and we do the printing, right? Yeah, var4 is basically the loop control variable, yeah, like I in the for loop. And Albert's asking, so based on the inc of the CMP value, can we conclude it's using a for loop? So that's the thing. We cannot always know for sure what kind of loop was used in the original code. It might have been a while loop, it might have been a for loop. It's how the compiler chose to convert it into assembly. But using a rule of thumb, I'd probably say that, yeah, most likely, knowing how programmers do things, probably this was a for loop. Make sense? And no, it doesn't really make a difference because it's not about getting the code right exactly. It's about getting the logic right. Make sense? Right? Oh, yeah. And once we're out of the loop, we have return 0. Yeah. So now let's take a look at the code for the proggy loop. So let's see what it actually was. And as you can see, it was indeed a for loop, which looped from I equals 0 until I is less than 10. And it printed out, I'm a little proggy. And then it exited. Make sense? Once again, folks, super duper powerful stuff. Yeah. Malware's life just got a little harder. Now, I want to try one more practice one before we get just a little bit more advanced and learn a few more things. So the next program which I want to look at is called Proggy Sub. It'll allow us to learn another important concept. All right, so just drag that in. And so like once again, you know, when I look at this program, what do I see right away? Something sort of jumps out at me. Do you see any signs of branching in here? Well, I do, yeah. And also, so basically, you know, let's see what's the story here. Now, also another thing which sort of jumps onto me is that there is a call to a function. Yeah, there is a call to a function. Now, it's not a function that is known to IDAPro. So either this is compiler generated code, but most likely it's not. Most likely it is the function that was part of the original program. So let's go ahead and let's analyze that and see where this gets us. So like once again, we will ignore all of this. This is just the stack setup. And what's going on here? So looks like, so what does this do? So we know we have variable var4, right? So we have var4 equals 1. Yep, very good, Joseph. And then what are we doing right here? What are we copying into EAX? The address, right, of variable 4. And Joseph has already recognized something. He says that, oh, look, really, what those two lines are trying to accomplish is, right, just increment var4 by 1, right? So really, we can replace all of that with just var4 plus plus, right? Yeah, and Lauren is correct about the LEA, right? It says move the address of variable 4 into EAX and then increment the contents of that memory by 1. All right? So basically, now, what's going to be the value of variable 4? So like this is where I'm going to keep track of my variables. It's going to be 2, right? Because once I increment 1 by 2, the value of variable 4 is going to be 2. Now, and over here, I have CMP, which compares the value of 2 against variable 4. Now, G and Z stands for jump, not zero. How does that relate? Well, basically, if you folks remember the CMP instruction, it is sort of like a subtract instruction. It'll subtract the right from the left, and if the result is 0, it will set the 0 flag to 1. Okay? Now, the difference between CMP and the subtract instruction is that the subtract instruction, it'll store the result of the subtraction in the destination. CMP will not do that. CMP, you can think of it as subtracting, in this case, 2 from var4, and if the result is 0, it'll set the 0 flag. Okay? Now, so because the values were hard-coded, and we know that the value of var4 is 2, right? So the result of 2 minus 2 is going to be 0. Therefore, the ZF flag is going to be set to 1, right? And the next instruction, G and Z, it says jump if not 0. Okay, so if the 0 flag is not set, it will jump to this location. Now, what's going to happen in this case? Well, do you think we'll go the red or the green? We're going to go the red route, right? Because why? Because the green arrow is going to be taken if the ZF flag is not set, but it is indeed set, right? CMP instruction has set it to 1. So therefore, we go the red route. So what happens when we go in the red route? We're calling a function. Ooh, so now this is getting interesting, right? This is the first time when we're calling a function in our own program, right? Where will this take us? Well, can we see the code of this function?
Can we go to function
Is there
on that calling, like that function name?
probably not gonna work. You know, so there is no way in which we can look in functions, unfortunately. In fact, advanced static analysis is kind of a you know, it's kind of a big joke. And none of that works, so we cannot do any more malware analysis. So if you don't have any questions, I hope you folks have a good one. You can master malware, and peace. No, I'm just kidding. I wasn't going to do that, right? Oh, good luck in your exam, right? Yeah. So in my OS class, I accidentally have actually ended the meeting. A joke that went too far, right? But yes, they were all able to rejoin, and probably they're telling stories about how weird their instructor is. And, you know, they say that he's weird. I'm not weird, I'm just creepy. There is a difference. Yes, so I think let's try clicking on it. Okay, so look, oh, look what IDA did for us. IDA has taken us to that function. Okay, now before we dive into this function, what I want to do is I want to go back to main just for a second. All right. So yeah, I'll do that in a second, Lauren. Yeah. So I want to go back to main for a second. Do you see how right after the call to this function right here, we're copying the value of EAX into variable 4. Sort of make a mental note of that in your mind, because we will go back to it once we talk about this function. So in order to go into this function, we can click, we just double click on it, and IDA is going to open that function. And by the way, folks, if this looks ugly to you, we can also rename the function. So how about we give it a more friendly name? You know, I'll call it foo, for example. Okay, boom. See, so now it is foo. So I'm going to double click on foo, and it takes me. So this is what foo looks like. All right, so what's going on in foo? Well, looks like we got our standard prologue, right? We're backing up the value of the EBP register. We're setting EBP register to point to the base of the current frame. We are subtracting 8 from the ESP, thus moving the value of ESP down to allocate space for the local variables. And now the fun part begins. Now, folks, you know, be careful. This var4 is different from the var4 in the main function, right? Those are local variables of foo. In fact, just to avoid confusion, I would suggest, you know, renaming them. So maybe let's call one cat and let's call the other one dog, okay? Just to not confuse them with, yeah, okay? Is that better? So now, so what is happening in this function? So it looks like we're copying, right, the value of 10 into dog and value of 5 into cat, as Joseph points out. Very good. So basically, so now we're inside foo, okay? So here we're doing cat, dog equals 10, right? And cat is equal to 5, right? Yeah, and then it looks like, as Joseph points out, what are we doing next? We're copying the value of cat into EAX, right? And then we are adding the value of dog to EAX, which contains the value of cat. So basically, we're doing cat plus dog, right? Cat plus dog equals cat dog. No, I'm just kidding. But that was a great cartoon in the 90s. So basically, EAX is equal to this, right? EAX is equal to the sum of the cat and dog. Now, this basically, once again, just restores the the value of EBP, and then we exit function foo. So where do we go from here? Well, we go back into main, right, which called foo. Now, and remember I told you to make a mental note of the fact that we're copying the value of EAX into the variable for in our main function. What exactly has happened here?
The function foo did the addition and then it passed it back in EAX.
Yeah, basically, function foo has returned, right, a value, and that value was returned in the EAX register. So basically, what happens right here is we called function foo, and we're now saving the value in variable for. So basically, we got something like this going on. So basically, we are calling function foo, and then we're saving the return of foo in variable for. Make sense? And then what happens after that? Well, it looks like after that we return 0. So it looks like we're doing, our code is doing something like this, right? So we begin by setting the variable for to 1, right? Then we increment variable for, and then we check, is variable for equals to 2, right? And if it's not, then we're gonna call function foo, right? So basically, and then we're doing something like this, var for is equal to foo, right? And then foo will basically add up the values of two variables, hard-coded values, and otherwise, if they are equal, then basically, we don't do anything. Okay, and then we have return 0. Does that make sense? And Lauren is asking, does this just retrieve the value of 15? Exactly. Yep. Foo will always return 15. Make sense?
Professor, I had a question.
Mm-hmm.
So in our code, does this actually reversing the if statement again? Is it doing the var for is not equal to 2, then go green, else if it's false, do red?
Yeah. I mean, I can also change it to that. Yep. So basically, I can do it like that. I can change the to not equal. Otherwise, basically,
I was just trying to make sure that I'm reading it correctly because it's a little bit it's inverse in a way. So I just wanted to make sure.
Yeah. And actually, it doesn't matter which way you do it because as long as you get the same logic. And actually, in fact, we don't know which way the original code was, right? It could have been either way, if you know what I mean. The compiler, when it generates the assembly, it basically just, it goes for the equivalent logic, and, it also does things like optimizing and things like that. But the point is, the logic is going to be the same, if you know what I mean. Does that make sense? And Zach is asking, is EX global since it's modified by foo? Yeah, all registers, they're always global, okay? Your CPU has a certain number of registers, EAX, CBX, CDX, CCX, etc. And yeah, I mean, they are effectively always global. But they're not stored in the data section. They're basically part of the CPU hardware. Okay, does that make sense? So that's basically the idea. So let's see. So we looked at, so this was Proggy Sub. Did we look at all of them? Did I want to look at anything else here? No. So basically those are our programs. Okay. So we've seen different examples. Now, what I want to do next is I want to look into something just a wee bit more advanced. Here I got another program called Mystery 1. So let's go ahead and let's take a look at that. All right, what does this mysterious program do? So I'm just going to drag it in, agree with everything that IDA says. All right. Interesting. Doesn't look like there's a whole lot going on here, right? So like once again, this code we can ignore. And then what is the next? So it looks like, what are we doing right here? So we're calling some kind of function, right? And what happens there? Well, then looks like we go right into return 0. So looks like right here, right? We got something like this. Now, folks, please though, don't forget about something. Okay, so let's just write down this logic really quickly, since I already mentioned it. So basically, it looks like we got something like this, right? Food. I'm sorry if I'm making anybody hungry, right? We can call it food. Hey, we don't know what the original function name was, so we can call it food, right? So now, one thing which I don't want you folks to lose sight of, yeah, we are covering a unit and advanced static analysis, but remember, you should always follow the proper procedure. Always do the basic static and the basic dynamic. And part of basic static is looking at the strings. Now, IDA is nice enough to show us. So do you see any interesting strings here? To me, they're jumping all over me right here. Right? So there is a string, right? Oops. Yeah, one string, another string. So there is, let's play a game, pick a number. Yeah, and Carla has found it in the data section. Yeah, look at that. And right away, I can see what looks like some messages. I also see some file paths, as Ian points out. Yeah, and I see the call to what looks like the remove function. So what I'm going to do is I'm going to click on this, right? And oops, let me come back. Yeah. So I clicked on the function, and it looks like I'm inside a function right now. All right. So where do we start with this baby? Well, let's talk about that. So over here, we have the following situation. So looks like we're pushing the value of EBP. So just your standard stuff, backing up the value of EBP, then setting EBP to point to the base of the current frame. Then it looks like we're allocating local variable space here. And then it looks like the interesting stuff begins. So now we're in, I'll call it, food. And I actually don't know if it's a void function or what it is. And it looks like, so what's going on over here? So it looks like we're setting variable 4, right, to 0, right? And what is happening next right here? Doesn't this code look familiar based on your previous experience? Right? What does it do? Yeah, so what does this whole chunk do when you look at it? Yeah, so basically it looks like we are doing what? Yeah, we're calling fprintf, right? And it looks like as a parameter, at least one of the parameters, we're loading the address of the string, let's play a game, pick a number. And then we got, basically, it looks like we're setting fprintf to the value of stdr. So basically it looks like we got something like this. So fprintf stdr, let's play a game, right? So and then and Lauren's asking, how did I know where you are right now? Where I am right now. Can you please elaborate? Oh, yeah, I'm in the third function. So basically, oh, I see the file name. Yeah, it's called advancedmystery.exe. It can be found in the mysteries directory inside exercises. There is the mysteries directory. So yeah, yeah. All right. So now, so looks like we are printing out, let's play a game and pick a number. Now, folks, you see how your experience comes in so useful. So now you're able to recognize entire calls to functions. Now, and what happens next? Well, I sort of look ahead and I see a call to scanf. And it looks like a bunch of stuff is being loaded into its parameter space. Now, what does scanf do? Well, it might be time for a little bit more, to do a little more research. So if I do scanf, and it takes me to what looks like a reasonable website. Basically, scanf can be used to get a value from the user, as Joseph points out. And it's actually a very simple kind of function. What you do is you call it a scanf, and then you provide a formatting string. So basically, the formatting string specifies the format of the data that you want to accept. So for example, what I can do is, if I expect my program to take a string as an input, what I can do is I can pass in a formatting string, %s, which basically means I want to get an input of a string from the keyboard, and when the user presses enter, it'll be stored in the second argument. But I can also directly get integers as input. So for example, I can do something like this: scanf %d, which basically means that I expect my input to be an integer, and then I can have int a, and then I just pass a reference to a like this. So basically, this will grab some input from the keyboard, and it'll store it in the integer a. So if the user types 1, then the value of variable a will be set to integer value of 1. So armed with this knowledge, let's take a look at what's going on right here. Well, if you remember, we always push parameters from right to left. So it looks like, what am I doing right here? So LEA, EBP plus var4 EAX. What am I doing here? I'm getting the address, right, of variable 4. Yep. And then what am I doing? I'm copying that address into the parameter space of the scanf function. So basically, folks, what I did was, so LEA basically got me the address of variable a, and then the move instruction copied it into the parameter space of scanf. So basically, I just took care of this parameter. All right. And then it looks like I'm copying the address of AD. Now, what's AD? Well, IDA is pointing out to me that it's a formatting string, which makes sense, right? So basically, it looks like I have a scanf function that looks something like this. And then it calls scanf. All right. So, and the reason why we knew that this was an int, because of this formatting string. So %d means that we'll be working with integers. Okay. I expect that whatever the user enters at the input will be an integer. So that's sort of like a giveaway. Okay. So basically, it looks like it will get input from the keyboard, and it expects the input to be an integer, and then the integer will be stored in the variable a. All right. So now, except of course, it isn't going to be variable a, it will be stored inside variable 4, right? So basically, what we have happening next is we have something like this: scanf and new line and var 4. All right, so we're getting input from the user. And what happens next right here? Well, let's see. So I'm just going to skip a few things down. So basically, right after that, it looks like I'm moving the value of variable 4 into EAX register. But then it looks like I'm loading parameter space again of some function. So I'm going to skip down, and I see another fprintf. So looks like EAX stores the value of variable 4, which we just got from the keyboard input, right? And then I'm copying the value of variable 4 into the parameter space of fprintf. And remember, we're doing things backwards. So fprintf. So it looks like the last parameter will be the value of variable 4. So whatever it is. Okay. And then we have, then next, we're moving the address of a formatting string used for printing integers. So %d without an end line in this case. And as we have seen before, like those 3 lines, that's basically a way of saying stdr. All right. So it looks like we are printing out whatever the user has entered. Yep, and ASCII is definitely correct, and Zach is correct too for agreeing. Right? Now, what happens next? So after the call to fprintf, it looks like we got a branch, right? We got branch. Like as in Michelle Branch, right? If you don't know who she is, that's perfectly fine. All right. So now, so we are comparing the value of variable 4 against 63 hexadecimal. What in the world is 63 hexadecimal? Well, I'll just convert in Python. So OX63, and it's 99. So it looks like we are comparing 63 against the value of 99, right? And then we have jump greater. So now, so jump greater will jump if variable 4 is greater than 100. So in other words, I'm going to go to the green arrow. Otherwise, I'm going to go to the red arrow. All right.
Professor.
So it looks like, yep.
Before we carry on, could I clarify something before I forget?
Sure.
On the fscan, on the scanf, was the EAX given EVP plus variable 4 as a pointer? Is that setting where to put the variable, like the value scanned in? And if we don't set that, if we don't set EAX and we leave it at 0, will we have to pop and pull, like push? Like, because I remember in 240 doing a lot of popping and pushing to do scanf. Is that a alternative method to do that?
Exactly. Yep. We'll talk about that today, actually. So there are 2 ways of passing parameters. One is the push method, and the other one is the move method. So this compiler, it seems that it's preferring the move method.
Right. And then the move method would be quicker because you're not going out of to the stack. Instead, you're just staying within the registers.
Well, you're still using the stack, right? Because I'm moving the value into the stack memory, right? I'm just not using the push instructions to do that.
Got it. So it's just the same thing, but different way.
Right, yeah. And, that's how the compiler chose to do it. This compiler likes to move it. Right? So, yep. So now, so over here we have a comparison, right? So jump if greater. So what I'm going to do is I'm basically checking is var4, if var4 is greater than 100, then I'm going to go toward the green path. So green. Otherwise, I'm going to go toward the red. All right. Now, so let's take a look. Let's take a look at the green first. Well, so I see that we are moving something into the parameter space of a function, which means we're getting to call something. And it looks like it's right after that, it's calling the function remove. How does the remove function work? Well, I don't know. That means research time. So, and I can always Google, Windows remove function. And there it is. Actually, I don't. No, that's not the one. That I was looking for this one. That's the one, right? So basically, it looks like this function. So it says it's basically removing a file. And as a parameter, it takes the path of the file to be removed. So basically, it takes in a pointer to the array of characters, which represents a path that will be removing. Yeah, very sus, right? So basically, it looks like it's copying the address of the string, and the string is C Windows System32 calc.exe. Why? Because IDA is being cool enough to tell us it's moving it into the parameter space of the remove function, and then it calls the remove function. What in the world does this do? Yeah, it's removing the calculator, right? So basically, it looks like it's doing something like this. It's calling remove with essentially this path. All right. Okay, it looks like my clipboard isn't working, but I'll just, path to the calculator, right? Yeah, so it deletes your calculator. And what happens next? Well, it looks like it's loading the parameter space of another function. So I'm just going to skip down a bit and see what function it's working on. And it looks like it's getting ready to call fprintf. So what is going to happen next? Well, it looks like it's copying the address of the string into the parameter space of fprintf. And then we know that this code basically means we're setting the stdr variable. So it looks like we got something like this going on, right? So we got fprintf. And once again, we always move parameters from right to left. And what's going to happen is, so the second oops, wait, what did I do? I escaped from the graph view. So basically, the second parameter is you did not need that anyways, right? Oh, this is getting juicy now, right? And stdr. Make sense? Right? Yeah. This is getting brutal, right? Yeah. And Joseph was asking, don't you need admin privileges to remove that? Well, not on Windows XP. Now, it turns out Windows XP does have a bit of a protection. It has something called SFP, System File Protection. Like, if you delete a critical file, Windows will basically, restore it. But no, you don't need any kind of admin privileges, right? So yeah, marking is totally fine. And then basically, after that, it looks like we go over here, and there is it looks like it moves the string of remove into the parameter space of the perr function, and perr is typically used for displaying errors. So it looks to me that it's some sort of an error check. All right, so if something goes wrong, then there is an error check right here. Doesn't look too exciting. But what I do want to know, though, is what happens when we go to the red. So what happens in the red? Please help me with the red. So yeah, and Joseph also points out, before we talk about the red, yeah, it looks like it keeps looping upon itself. Yeah. In case of an error, it ends up looping upon itself. Yeah, it goes into an infinite loop. That's true. Yep, it'll print it out forever. Yeah, it's not actually, yeah, so, and then if we go to the red, right, so what's happening right here? So first, as some of you are saying, it calls the fprintf function, right, with a string zeptim good. So fprintf stdr, yeah, zapped him good. All right, and then it looks like we are copying, as Danny and Joseph and many others point out, it looks like we're copying the address of this path, which seems to be pointing towards a Firefox executable, right? And we're calling the remove function on that. So basically, it looks like we are doing remove and basically path to Firefox. All right. And then after that, it looks like we jump right here. And this looks like return 0. Well, actually, I'm sorry, this is not return 0. We're not in main. We are in another function, right? Because remember, the program began with a main calling another function. So this is just us cleaning up EBP and returning back to main. So basically, folks, I think that's what we got. Yeah, that's all that it takes to delete this. Now, before we take a break, let's let's summarize what this program actually does. So, anybody want to take a step at summarizing the overall logic of this? Yeah, it plays a pretty brutal game, right? So it asks the user for a number, right? And if the input, as Joseph says, greater than 100, then it deletes the calculator. But if it's less, it deletes your Firefox. So basically, this program kind of plays a brutal game with the user. Depending on what number you enter, yeah, it's basically, like Lauren points out, you always lose. It's it's how you lose. Yeah, that's true, unless you use Chrome. Right, yeah. Or if you use Linux, then those paths will be invalid. Right? Yeah. Oh, yes, it is 99. Yeah, thank you. Yeah. Now, before we go on a break, let's actually see how close we got. So let's take a look at the source code and see what we got here.
I think it's actually 99. I think.
Oh, it should be 100. I don't.
Yeah, because 99 would have been if it was inclusive, but it's exclusive.
Yeah, you're right. Actually, yep. Thank you for Yep, you're right. Yeah. In the code, it said 99, but logically, right, we're testing if var4 is greater than 100. Now, so it looks like we actually, so it looks like we did get the right logic, but our code is sort of backwards, right? So basically, it looks like in the original code, it checked is num. So num is basically var4. We cannot know its original name because that's lost in the compilation process. So if the input is less than 100, then it's goodbye Firefox, right? And we got that figured out. And if it's greater, then basically, if it's greater than or equal to that, then it's goodbye calculator. So basically, we got the same logic, just just a little bit of different code. Okay. So basically, what the original code did was it had the sign backwards and then just swap the order of the if and the else. But the point is, we got the logic right. And of course, food was actually named getNum. I mean, again, all that information has been lost in compilation, right? In order to cause discombobulation, right? All across the nation. What a sensation. Okay, I'm done. All right, so do folks have any questions before we go on a break? And I know I went well. I went well over the break, but yep. So no food. The cake was a lie. Okay. Oh yes, and there is another one. IDAPro. It's only a game. Yeah, and did we see that anywhere? Let's see. Yeah, looks like. Yes. So looks like, folks, the version which I have on the screen, it's a slightly updated one. I added that one later, but it looks like I didn't, I didn't compile it. That's a good catch, yeah. But if I compile it again and I drag it in, the string will definitely be there. Yeah, that's a good catch, Justin. Yeah. Yeah, so that's basically the idea. So let's go ahead and let's take a break, and then we're going to come back and we will talk about the parameter passing conventions, and also we will talk about linked lists, structs, and all that great stuff. All right. Yeah, I guess we could do one more program. Yeah. Yeah. Or maybe we can do that for class. We'll see. We'll see. Yeah. All right. So let's go ahead, folks, and let's take a 10-minute break, and then we will talk again.
Professor, could I ask you a question?
Sure.
So this is on exam 1, obviously. So would you expect us to be writing the C++, or would we just be writing out like a written format of what's going on?
Just a clear description of the correct logic is fine. The reason why I'm writing it out in C right now is just, to sort of, I understand, that I'm dealing with people who have never seen the stuff before. So I'm sort of trying to, to use it as an explanation tool. But yeah, on the exam, just providing a correct and clear explanation, that's perfectly fine. I mean, yeah, because in the real world, that's what you're going for, right? I mean, right. Because like, let's say that, I'm just using this as a teaching tool, basically.
Okay, and then so if we just write it in code for the exam, that would be also okay, right? Since that's more concise than just writing out what it's doing.
You can use that, definitely, yeah. You can use that as an explanation aid. But like if you said like something like this, this program plays a game. It asks, the user to enter a number. If the number is, what was it? Greater than 100. What is it? What does it delete?
I think it's so Firefox or Chrome.
Yeah, it prints, basically, whatever the message, and deletes, the calculator. You get the idea, right? Otherwise, yeah. Yeah. So basically, I did have some fun answers in the past. I had answers like this program executes a bunch of instructions on the CPU to implement a logic. It looks really beautiful. I'm sorry, Dr. Guffman. I mean, I blanked out. So, yeah. So, I mean, I'm glad that some people at least they have an aesthetic appreciation of assembly. Yeah. And Justin's asking, how do we work out hexadecimal numbers for the exam? So there are many ways in which you can do it. Like me, you can use the Python if that's what appeals to. In Python, basically, you do this in your terminal or however it is you start Python prompt in your system. You would start Python, and if you want to convert a hexadecimal number to integer, you type OX, which tells Python you'll be working with hex numbers, and then you type a hexadecimal number, for example, 63, and then you just press enter, and it'll give you base 10. If I want to convert a base 10 number into hexadecimal, I just type hex and a base 10 number, and it'll give me the hexadecimal equivalent. You can also use the Windows calculator if you want to. So Windows calculator can do the conversion too. Let's say that I want to convert 100 into hexadecimal. By the way, you want to go to View and Scientific. I have already done that because by default your calculator will look like this. So you go to View, Scientific, and then if you want to convert from base 10 to base 16, you would choose decimal, and you type the base 10 value, and then you click on hex. See, it gives you the hexadecimal value. Similarly, if you want to convert from hex to base 10, you would choose hex right here, then type the hexadecimal value, for example, 64, and then click decimal, and it will give you the value. Yeah, it's not installed on the VM, but if you want to use it on your host system, or even, I can send you an online Python prompt, you can do that as well. All of those are valid tools. So why did we put 100 instead of 99? So it was 63, right? So 63 is 99. But logically speaking, it was equivalent, right? Logically speaking, it is equivalent, if you know what I mean. Right? Because here it said jump if greater than 99. So if greater than 99, delete the calculator, which is the same thing as as saying that greater than less than is it greater than 99?
I think we're missing an equal sign.
Yeah, there we go.
Well,
Yeah.
in the C code you showed, the if was reversed, and it was if the variable was less than 100, I believe, right?
Yeah, yeah, I think.
Showed.
Yeah, yep, that's a good catch. Yeah, yeah, yep, that's a good catch. Yeah, because the opposite of this is greater than or equal to. Yeah, yeah, and also notice like here. So basically, our signs are reversed, but also the statements are flipped. So therefore, the logic is equivalent. But I did miss the equal sign. That is a good catch. Thank you. The devil is in the details, as they say. All right. All right. Great. So before we jump back, let's learn a few more things that are sort of important in our malware analysis. So the next thing which I'd like to talk about is how to recognize certain constructs in assembly. So it turns out that function calls can be done in different ways. Those are called function call conventions. And depending on what functions you're calling, it will be determined by the compiler. Now, when we talk about function call conventions, we're talking about the order in which the parameters are pushed onto the stack, and whose job is it to clean up the parameters on the stack once the function has returned. In other words, should it be the caller function that cleans up the parameters which were passed to the callee, or should it be the callee that clears the parameter space? So let's dive a bit deeper into this. Turns out there are three different function call conventions. They are CDCL, STD call, and fast call. Let's talk about those. So basically, let's talk about CDCL first, and this is one of the most popular conventions out there. So in a CDCL, parameters are pushed from right to left, and then once the function finishes, it is the job of the caller function to clean up the parameter space. And the return value is always stored in the EAX register. Let's take a look at an example. Let's say that I have this code where I have function test, which takes parameters x, y, and z. And over here, I'm calling function test, and I'm passing some local variables a, b, and c to that function. And the function is returning the value, whatever it is returning, and we're storing it in the integer variable called ret. It can look something like this. So first, we're going to push the parameters. So basically, we have, we're pushing them from right to left. So first, we push C, then we push B, and then we push A. Next, we call the function test. So function test will execute, do whatever it needs to do. But now, we have pushed 4 parameters onto the stack. So the question is, how are we going to clean them up? So basically, here is the stack. So here, I pushed C, then I pushed B, and then I pushed A. All right. So what's going to happen is, what happens next? All right. And so, well, right now, my ESP register is pointing to the top of the stack, as it always does. And then once the function returns, once call returns, we need to deallocate the space. So how do we do that? Well, in this case, we are just subtracting 12 from ESP because we pushed 3 integers, right? And the 3 integers are each 4 bytes in size. So to deallocate their space, we are subtracting 12 from ESP. So in other words, in the CDCL convention, it is the caller that cleans up the parameters. And we can see that happening right here, right? Because right after the call to test, the caller deallocates the parameter space. We can also see this part as well, because test copies the return result into EAX, and then we are basically moving EAX into red. All right? Does that make sense? Yes, Joseph? Mm-hmm.
So if we were to add ESP12 and then we try to access the push C, B, or A, is it possible we'll still see those values there, but it's also possible it could be something else that's taken over that space already? But it's like a 50
right, yeah,
right?
Yeah. Basically, when we add, if I said subtract, I'm sorry, but like when we add to ASP, we're basically dragging ASP back up. But yeah, any data there, I mean, it'll stay there until it's overwritten by something else. Yeah. Mm-hmm. And the fourth parameter, I don't think we have a fourth parameter in here anywhere. I think we just have 3.
Oh, I got confused because you said 4 at first, but I assumed that's what you meant.
Oh, I'm sorry. Yeah, 3. I meant 3. Yeah, I can't count. All right. So this is basically the CDCL convention. Okay. So once again, push parameters in the right to left order. The caller is responsible for deallocating the parameters, and we store the return value in the EAX register. Now, the second convention, STD call, is actually very similar to CDCL, but there is one important difference. So in STD call, the difference is that instead of the caller cleaning up the parameter space, it is the job of the callee. So if we compile this code and the compiler uses CDCL, okay, we will see something like this. In the caller, we will see add ESP12, which will deallocate the parameter space. In the callee, in the STD call, we will not see this code in the caller. Okay, we will see this code in the callee function. Now here, I'm not showing you the code of test, but if we looked at the code of the test function, we would see something like this. So basically, CDCL and STD call are identical, with the difference that in STD call, the callee cleans up the parameter space, and in the CDCL, it is the caller that cleans it up. All right? Does it make sense? Do we have any tricks remembering which one is which? I sort of just done it so many times, like I kind of remembered it, but yeah, yeah. Now, and another one is called fast call. Now, this one is going to be easier to remember. So fast call is the fastest way to pass parameters. That's why it's called fast. So it's basically very similar to CDCL, but the difference is that the first few parameters are passed through registers. So for example, if my function took, for example, say 5 parameters, I would pass, for example, the first 3 parameters by moving them into registers instead of pushing them onto the stack. And then the rest I would push onto the stack. All right. And why is it fast? Well, because registers are the closest memory to the CPU. So hence passing arguments through registers is extremely fast. And whenever I push something onto the stack, I have to access the main memory, and that has greater latency because that's farther away from the CPU. All right. And similar to CDCL, the caller will clean up the stack, and it is the fastest of the 3 conventions. So basically, folks, fast call is the fastest. Okay, that's a good trick to remember. All right. So any questions? Are we good? CDCL, caller cleans up. Oh, I like that. I like Carlos' trick. Caller cleans up the parameters. I like that. Yeah. So now Before we look into more advanced data structures, let's take a look at two ways of passing things as parameters. And this question was already brought up by one of you, because you said when you took 240, you pass parameters by pushing. But when we looked at our examples, there was a lot of moving. Well, it turns out that both are valid ways of doing this. Let's take a look at a piece of code where we do things by pushing and by moving. So here we have a piece of code where we have the main function with local variables x and y. X is equal to 1 and y is equal to 2. So then the main function calls printf, which prints the function returned a number and an integer, and it prints whatever was returned by the function called adder xy. So, and the adder function just takes two parameters, a and b, it adds them together, and then returns the value. So this example shows you the difference between the push and the move. So this code has been compiled using two different compilers. The code at the top was compiled using Visual Studio, and the code at the bottom was compiled using GCC. Let's see what is going on here. So it looks like the Visual Studio code is using push. So we have this kind of a scenario going on. So originally we got our stack, and ESP is pointing to right here. Okay. So now, yes, there is stuff before that, but let's not worry about that. So it looks like we're moving the value 1 into variable 4. So it looks like we're doing this part. Then we're moving the value of 2 into variable 8. Again, we're doing this part. And then the interesting stuff begins. Okay. So we're getting ready to call the adder function first. So what we are doing right here is, it looks like we're pushing the value of variable var8, which is y, onto the stack, right? Then we copy the value of x into ECX, and then we push ECX onto the stack. So basically, our stack now looks like this. So something like that. So first, we pushed on our value of y, and then we pushed in our x, and then, of course, we have to advance our ESP to point to this, okay, to the top of the stack. All right, so, and then we call the function adder, and then we deallocate the parameters in the caller by doing add 8 to ESP. And because those are integers, when we add 8, basically ESP gets moved up here, and that's the space is deallocated. Okay, and then it looks like we are pushing the EAX to the stack. Now, folks, what does EAX contain at this point? Well, it contains the return value of adder, right? So we're pushing that onto the parameter space of printf, and then we're pushing the format string %d to the parameter space of printf, and then we call printf. All right. So that's basically the idea. All right, and we're actually pushing. So the first thing which we're pushing in this case is y, right? Right, because we always push from right to left, right? So basically, so y is var8. So first we moved the value of y into EAX, and then we pushed EAX, and then we moved the value of x, var4, into ECX, and then we push that. Okay, so that's basically the idea. So this is the push approach. Now let's take a look at the move approach, which really accomplishes the same thing. So here is our stack, and let's say our ESP originally points to this. Again, the beginning part is actually pretty, simple in a sense that same thing, we copy 1 into X, we copy 2 into Y, and then we copy the value of Y into EAX. Now, here is the thing. So we're doing ESP plus 4. So ESP plus 4 basically is going to reference. So basically, we're going to skip this, basically, so we go this way. So ESP is now pointing to right here, and then we got a 4 bytes gap in between. Now, and then into there, we're moving the value of EAX, which stores the value of Y. And then we're basically, now remember, we haven't actually moved ESP. ESP is still pointing to the beginning, right? The way in which we ended up accessing this memory, we just did ESP plus 4. So really, we added a value of 4 to ESP, but we never updated the value of ESP. So we moved the Y in there. And then the next thing, it looks like what we're doing is we are copying the value of X into EAX, and then we are copying the value of EAX into what ESP is currently pointing to. So basically, we end up with an X right here. Okay, so basically, they end up achieving the same thing, just in 2 different ways. Does that make sense, folks? Right? So in both cases, we end up with pretty much the same stack, but one uses push and the other one uses move. Which one is more efficient? It depends. It depends. So they're about, I would say, the same level of efficiency. Yeah, because both of them are passing the parameters through the stack at the end of the day. So both of them are accessing main memory. So I'd say they have about the same performance. Just 2 different ways of accomplishing the same task. All right. All right, great. Now, the next thing which I'd like to talk about is, compiler will decide which one is going to be used. The next thing which I'd like to talk about is something that is frequently being done in backdoors. Okay, backdoors make use of the case switch statements, and we're going to review those in 1 second. But basically, there are 2 ways of implementing case switch statements. One is using the if style, and the other one is using the jump table approach. So let's talk about that. Let's say that I have a piece of code like this. So first, let's take a look at the if style implementation of case switch. So I have the value of I, and if the value of I is 1, then this code beneath case 1 is going to be executed, in which case it'll print the value of I plus 1 and then stop and move on. If the value of I is 2, it'll print the value of I plus 2, then stop. If the value is 3, it'll print out the value of I plus 3 and then stop. Otherwise, it'll just go to the default and not do anything. So how would this code look like if we compiled it using the if style? Well, let's take a look at that. So this is the resulting code. So it looks like we are copying into the variable, into the memory of local variable 8, the value of 1. So basically, it looks like I is represented by variable 8. So variable 8, and I'm going to in parentheses put I, just to keep things in perspective, is equal to 1. Actually, I'm sorry, no, we are not setting it equal to anything. So basically, So it has some kind of value. We don't know what it is. And then we have the CMP statement. So it compares, is the value of I 1? Okay. And then it has JZ. Okay. So if the value of I is 1, then basically, 1 minus 1 is 0, and JZ is going to be set. So this jump is going to be taken if the value of I is equal to 1. So where are we jumping in this case? Well, it looks like we're jumping to the memory location of 401, 207, 1. So, I'm sorry, 401, 0 to 7. So it looks like it's going to jump right here. And what is happening right here? Well, it looks like we're copying the value of var4 into ECX. Now, what in the world is var4? Well, folks, we'll have to assume that somewhere in the code before, var4 was also assigned to equal to I. Okay? So basically, we can assume that var4 is equal to whatever I was equal to. Okay? Now, we just don't get to see it. Assume this happened, sometime before this code was invoked. And then the next thing which happens is, so it moves the value of variable 4 into ECX. So ECX is going to equal to, so let's say it's going to equal to 1, okay, since we're taking this jump. Then it will add 1 to ECX, which basically increments it by 2. And then the next thing which it does is it pushes the value of ECX onto the stack. So basically, it just pushed the value of I plus 1 onto the parameter space of printf. Next, it pushes the address of the formatting string %d onto the stack. And then it calls printf, which will print the value of I plus 1. Then we are deallocating the space we allocated for the sum and for the pointer to the string, because we are doing CDCL. And then we jump to location 40167, which is outside of this code. So basically, this is a way of implementing break. Okay, so we are jumping out like beyond this code, so we don't go ahead and execute the instructions for the other cases. Let's take a look at another case. Now, let's say that the value of our 8 is actually 2. Okay? So now, in this case, wait, how did you know that we're doing CDCL? The reason why I know we're doing CDCL is because I saw add ESP8, and that basically means that because it's being done after the call to printf, it means that the caller is cleaning up the parameter space. So therefore, we're doing CDCL. And I know it's not fast call because we haven't passed any parameters through the registers. So yeah, so basically it's CDCL. So now, let's say the value of I is 2. Well, we do CMP of I of 2 to 1. They're not equal. So JZ is just going to be skipped. And then we do CMP of 2 against 2. Now they're equal, and we jump to the memory location of 401, 0, 3D. So basically, we end up jumping right here. Again, we'll assume that variable 4 was set to I as well somewhere in the code. So in this case, we're setting the EDX register to be equal to var4, which is the same thing as var8. So it's equal to 2. Next, we increment EDX by 2. So EDX is now 4. And then it looks like we're pushing the pointer to the format string, I equals D, onto the stack of the printf, and then we call printf, which will do the printing. And then again, we jump to location 40167, which is beyond this code. So that's how we implement break. Does that make sense? And also, now let's say that same thing is going to happen if it's 3. In that case, this jump is going to be taken which will jump to location 40153. So basically, it'll do same thing, you know, add 3 to I, you know, push the sum to the stack, push the pointer to the format string onto the stack, and then call printf and deallocate the parameters. If none of those jumps end up being taken, then basically I will just take this jump, which will simply jump out of this code. So in other words, that's how we implement the default, all right? And yeah, so, and just asking, if you see a stack of compares, it is either else or switch case, exactly. And do you see why it's called if style, right? Right, because, you know, essentially, yeah, you know, we're sort of simulating an if statement. All right. So this is the if style approach. Now, there is also something called the jump table approach. So the issue with the if style approach is that it results in a lot of comparisons. The jump table approach can reduce the number of comparisons, so, but still achieve the same logic. So let's take a look at that. So we have the same code, which was now compiled to use jump table. Now, folks, do you see this right here? This is my table, okay? And this table is stored in memory. It's kind of like an array. And this array consists of the memory addresses to which will be taken jumps. All right. And the size, because each memory address is 4 bytes, the size of each slot is going to be 4 bytes. All right. And each slot contains an address to which we can jump. So I'll call address 1, address 2, etc. Okay. So, and those are the actual addresses. So now, the way in which it works is as follows. So once again, you know, let's assume that in the beginning of this code, the value of I is passed inside of the ECX register. So in other words, ECX is going to be equal to whatever the value of I is. So let's assume that the value of I is, whoa, what happened? Let's assume that the value of I is 1. What's going to happen? Well, I subtract 1 from ECX, which makes it 0. And the reason why we want to do that is because arrays begin at 0. So we want to decrement that by 1. So we start at 0. Then we're copying the value of ECX into variable 8, into local variable 8. So it's going to be 0. And then we are comparing. Is 0, we're comparing 0 against 3. And then if 0 is above a 3, then we are going to jump to this location. Okay? But in this case, it is not above 3, right? Because 0 is less than 3. So what we end up doing is into the EDX register, we move the value of var8. So EDX is equal to var8 equal to 0. And here is where the jump table logic comes in, folks. Now, if you see DES, it means this table is stored in the data section. And it begins at this offset, okay? So basically, I'm going to go to find the beginning of this table, I'm going to go to my data section. So I'll go to offset of 401088 in my data section. And then that's where this array begins. Now, folks, in x86 assembly, all indexing is always done in units of 1 byte. But each address in this array is 4 bytes. So if I want to jump to address 0, what I'm going to do is I will multiply 0 by 4, which is equal to 0, right? So I'll be accessing the beginning of slot 0, which contains this jumping address. So basically, I'm going to jump to whatever is stored in that slot. So I'm going to jump to address 4012C, which is right here, where the appropriate computations will take place. And then I call this jump, which will jump out of this code. Let's take a look at a case where the value of ECX is originally 2, because that's a bit more interesting. All right, so we're going to decrement 2 by 1. So basically, now it's going to be 1. Then we copy ECX to variable 8, making that 1. So then we compare ECX against 3. So basically, ECX is not above 3 because 1 isn't above 3. So basically, this jump doesn't take place. So next, into the EDX register, we are going to move the value of variable 8, which is 1. Now, here is where the interesting part comes in. So we're going to go into the data section to this offset, and then from that offset, we want to access byte number 4 times 1, which is 4. So folks, each slot is 4 bytes. Yeah, it's going to take us to the second index, as Alex points out. So basically, 1, 2, 3, 4. So that takes us to the beginning of the second index. And this is the second index, which contains that address. So we're jumping to that address. So, and that address is 40142. So we end up going, where we go? And we end up going right here. So then we execute all the code, and then we take this jump, which jumps beyond this code. Okay, make sense? Well, actually, it's not going to jump beyond this code. It'll jump right here. Okay, it'll jump to this part of the code, which basically just contains the function epilogue. Okay, so once each piece of code is done, it'll jump to this address, which contains the function epilogue. So basically, it exits the function. Does it make sense, folks? Do you see how we were able to completely avoid making comparisons, really, right? So we use I as an index into the array of jump addresses, and we basically find the appropriate address, and we jump right to it. All right? So do we have any questions?
I still don't understand how you know which is the appropriate address. Like, where can you make that decision?
Oh, it's being made right here, right? Like basically, so what I'm doing is, based on the value of I, essentially what I end up doing is I end up indexing into this array based on the value of I. So if value of I is 0, right, I will be indexing into the first slot. Yeah. And the first slot contains this address, and then this jump instruction will jump to whatever that address is, right? So it'll jump right here. If the value of I is 1, then I'm going to index basically 4 bytes after the beginning, right? That's why I multiplied by 4, because each address is 4 bytes. So I'm going to go to the second index, right? And then I'm going to jump to this address. Make sense?
Got it. So
yeah, so that's basically the idea. Are we good? Make sense?
So basically, we're taking that single compare and we're putting it into a variable to be able to, based off of the indexing on that compare, we can go ahead and do our different jump table. And
right.
The index is always the same because the index is dependent on 0, 1, -1 kind of idea.
That's right. Yeah. In this particular case, yeah.
Got it. Thank you.
Make sense? Yep. Sure. Yeah. So that's basically the idea. Now, the next thing which I'd like to look at, and by the way, I did annotate all of that for you. The next thing which I want to look at is the arrays. Okay. let's take a look at how the arrays are implemented, because that's very, very important, and you will see things like that in quiz 1 all over the place. So here I have some code and I have two arrays. One is a global array and the other one is a local array. Both are 5 integers long, and each integer is 4 bytes because we're on a 32-bit system. And then I have a loop which goes from 0 to 5, and it basically sets each index of each array to the value of I. Let's see how this code is going to be implemented, or how it's going to be compiled. So it looks like we are moving the value of 0 to var18. So basically, I can conclude that var18 is probably I in this case. All right. So it's equal to 0. Then it jumps to location 40118. So in other words, it jumps right here. So what's happening right here? Well, we're moving the we're comparing the value of variable 18 against 5. Okay, and if I is greater than or equal to 5, then we're going to jump to location 40137, which looks like is a location outside of this code. So in other words, we basically, we're done with the loop if I is greater than or equal to 5. Otherwise, into ECX, we're moving the value of variable 18. So ECX is equal to 0. Then we're also into EDX. We're moving the value of var18, which will make that 0. And then, oh my God, what is this? Now, it looks like because I see an EBP in there, we are moving in a local variable. Okay, it's a local variable. Now, if only we could rewrite it in a way that it's less scarier. So what if I write it like this? So EBP plus var14, right? This is just a regular way to refer to some local variable. Okay. Now, of course, IDAPro probably, that's what it means by that. And then to that, we're adding the value of ECX times 4. Now, what is going on here? Well, folks, you may have probably guessed already, but here we are indexing into the local array. So it looks like our local array begins at the local memory address of EBP minus 14, and we want to access slot ECX times 4. Because remember, this is an array of integers, and each slot is 4 bytes. So originally, ECX is 0, right? So 4 times 0 is just going to be 0, and that plus that is going to be just EBP minus 14. So basically, I'm accessing the first slot of that array. Okay? So basically, and what happens next? So into the first slot of this array that begins at address EBP minus 14, I'm copying the value of EDX, which is 0. So, and then what am I doing next? Well, it looks like then into the EAX register, I'm copying the value of I again, which is 0. And then it looks like I'm also copying into ECX the value of 0 again. All right. And then here is the interesting part. Now it looks like we're populating our global array. So let's say this is my global array. And it looks like my global array begins at offset of 40A000 in the data section. Okay. So what's going to happen next? Well, it looks like starting from that address, I want to access an offset of ECX times 4. Now, I mean, once again, ECX is 0, right? So 0 times 4 is going to be 0. So I'm accessing it at the beginning at location 0, and I'm copying the value of EAX into that. Okay? EAX, or 0. Okay? So that's basically the idea. And then what do? I jump to location 40100F, which is basically right here. And what am I doing now? Well, I'm comparing. So I am, well, okay, I'm not yet comparing. I'm actually moving the value of I into EAX. Now, I is still 0 at this point. So EAX is going to be 0. And then I add 1 to EAX. All right. Then I copy EAX into var18, which represents I. So now we are at I equals 1. And then we compare, is 1 greater than or equal to 5? Well, it's not. And we now repeat this whole saga again. Copy the value of I into ECX. Next, we copy the value of I into EDX. Then we copy the value of EDX into the local array, which begins at location EBP minus 14, right? Plus ECX times 4. Now, because ECX right now is 1, so this whole thing will end up being 4, right? So basically, we're starting at this local address, and then we're doing 4 bytes. 1, 2, 3, 4. Again, each integer is 4 bytes. So now we're pointing to right here. And into that, we're moving EDX, which is 1. And then after that, I mean, again, I move the value of EDX into, I'm sorry, I move the value of I into EAX. So nothing really changes because that's already 1. Then I move the value of 1 into ECX. Again, nothing changes because, well, it's 1 again. And then I move the value of EAX into the offset starting at memory address, at this memory address in the data section. So ECX times 4. So ECX is 1. So 1 times 4 is 4. So we're starting at location 4. So 0, 1, 2, 3, 4. And we're starting at the beginning of this. And we're moving EAX into there. So basically, EAX is 1. And then, once again, story repeats. We jump back to this address, increment I, and keep doing this until everything works out. Does that make sense, folks? So not so bad, right? Yeah, so looks like we're out of time, and I didn't get a chance to get to linked lists. So I guess, to be fair, I'll have to take it off the exam 1, and I will put it on exam 2. All right? Is that fair? Right? Yeah. So and then so yeah, and in the review session, I so I have covered this much slowly and a lot more detail. And in the next review session, we'll cover what are we covering? Basic static and basic dynamic. But if you want to, we can maybe do another executable or two. And also, folks, and we're out of time. You can go if you want to, but please try quiz 1 and quiz 2 before the exam. It'll definitely help you prepare. Okay, so yeah, all right. And Carla started quiz 1, and that's cool. Do you want to be cool like Carla? Well, you can do it too. All right. So Shmiket has already finished the quiz in his head. Yeah. All right. So any questions, folks? I'm in the Q&A mode, by the way. All right. So, all right. So questions. And Carl's asking, Can we use malicious code in the IDE? Yeah, yep, absolutely, yep. Yeah, that's one cool cat, yeah. Yeah. All right. So, and also, you can practice on mysteries as well. In fact, folks, for those of you who want to, I don't mind like doing another executable right now. For those of you who are interested, would you like to try one more executable right now, like one of the mysteries? Yeah, sure. All right. Yeah, we can definitely do that. All right. So let's try another mystery. So, all right, but you'll have to help me. Okay, there we go. So looks like we got another mystery program. Oh, this is actually good because it'll give us a chance to review something. So as we talked about before, right, this is just the compiler code that sets things up, that sets the stack up. And also, when I look at this, what do I see? Well, I see that we got some kind of a branch, and then we have an unconditional jump. So whenever I see something like this, it usually means that we got ourselves a loop. Okay, we got some sort of a loop situation going on. So, but first, let's go ahead and see what's going on. Well, it looks like we begin by moving the value of 0 into var for C. Let's give it, let's see, var for C is basically minus 4ch, of course. Do you want to give it some kind of another name? Like just to practice renaming of variables, I can do rename. And, let's call it, so when I look at this, it looks like some sort of a loop control variable. So let's call it meow. Okay, let's call it meow. I don't mind. Yeah. So basically, we begin by moving, by setting the variable meow memory to 0, right? We can see it right here. And then we go into this code where it looks like we're comparing the value of meow against E. Now, I actually don't need Python for that, but just to practice, to convert from hexadecimal to decimal, I just type OX and then my hexadecimal number. And it's basically 14. Once again, I didn't need Python for that, but, just wanted to sort of reinforce that. So basically, it looks like we are comparing to see if meow is greater than 14. Okay, so if meow is greater than 14, then it looks like we're gonna go into the green. Okay, and the green looks like basically, what does this look like again? So we're in the main function. So this looks like a what? So we're at the end of the function and we're copying 0 into EX and we're calling leave to restore the stack and then we're calling readN. We are basically doing what? We are returning 0, right? So basically we have something like this. Return 0. Otherwise, if it's not greater, then we go into the red arrow. So the red arrow does the following. So let's see what happens inside of here. So it looks like into the EDX, we copy the value of meow, and the value of meow is, at this point, it's 0, right? And then it looks like we then copy the value of meow into a EAX as well, like that. So we have EAX. All right. So, and then it looks like we add them together. So we do. So we add EAX to itself. Now it is still going to be 0, right? Because, well, it's 0, right? So, and then what do we have right here? Oh, doesn't this look familiar? Right? What does this look like? Yeah, it looks like an array, right? Because, like, once again, it looks like we're, so if meow is our index, because that's what it looks like from here, then it looks like we're traversing an array of 4-byte quantities such as integers. And like once again, if that looks scary, you can always rewrite it like this, right? So EBP plus var 48, right? And then to that we're going to add the offset of EDX times 4. All right. But of course, EDX is 0. So, I'm sorry, yes, EDX is 0. So basically, we end up, so all this is 0, we end up accessing the local memory of EBP plus 48, which is the same thing as EBP minus the value of 48. So, and into that place, it looks like we're moving the value of EAX. So basically, looks like we got something like this going on. So into the location of EBP minus 48, which looks like it is the first thing, we're moving in the value of 0. All right. And what happens next over here? Well, it looks like we are loading the address of meow into EAX. So we're getting a pointer to meow, and then we're incrementing the 32-bit value stored at the memory location pointed to by the pointer. So what am I doing effectively? I'm basically incrementing, right, meow, right? So now meow is going to be equal to basically 1, right? So, and then right after that, there is an unconditional jump, whoop, which takes me back right here. So now again, I check, is 1 greater than 14? The answer is still no. So we take the red arrow and we go right here. Again, into EDX, we move the value of meow. So basically, my EDX, all right, so EDX is going to be equal to 1, right? And then EAX will also be equal to 1, right? Then we add EAX to itself. So basically, 1 plus 1 is equal to 2, right? So, and then we copy the value of EAX to the location of EDX times 4. So basically, we're starting at this address, which is EBP minus 48, but then to it, we're adding EDX times 4. Since EDX is 1 and 1 times 4 is 4, and we're basically moving 4 bytes, 1, 2, 3, 4, from the beginning of the address of this. So it looks like we're now looking at the second slot of the array, and in it, we're going to be storing the value of EAX, which is 2. Okay? Like that. And then, again, I load EAX with the address of meow. Then I increment the value that is stored at that address. So basically, meow is now 2. And then again, I jump right here. So then I compare. Is meow, which is 2, is it greater than 14? Well, the answer is still not. Well, it's the red arrow again. So EDX is loaded with the value of meow. So EDX is equal to 2. Then EAX is loaded with the value of meow, which is now equal to 2. Then we add EAX to itself. So 2 plus 2 is 4. And then we are going to copy the value of EAX to an offset of EDX times 4 from the base address of EBP plus 48. So 2 times 4 is going to be 8. So we start at the beginning and we move 8 bytes ahead. So 1, 2, 3, 4, right? 5, 6, 7, 8. So basically now it looks like we're looking at the next slot. and in it we store the value of EAX, which is 4. Do you see a pattern emerging here, folks? Anybody sees a pattern, right? Yeah, it looks like it into each slot, it is moving the value of I plus I, right? So into each slot I, it moves the value of I plus I. Just to just to make sure. Let's do another iteration just to be sure. So basically, we take a jump to the beginning. We compare his 2. Oh, and I forgot to increment meow. So meow is now going to be 3. I skipped that part. So right before we took a jump, we incremented I to 3. So we move. So we increment meow to 3 right here, and then we take a jump. So, and then right here, I compare, is 3 greater than 14? Well, it's not, so it is the red arrow again. So basically, I mean, again, EDX is loaded with with meow. EAX is loaded with meow. Then we add EAX to itself, and this will give us a 6, right? And then we move the value of EAX, which is 6, to an offset of EDX times 4, which is 3 times 4, from the base of EBP plus 48. Okay, so we do 3 times 4, which is 12. So we start from the beginning, which is the address EBP plus var 48, and we go to an offset of 12. So 1, 2, 3, 4, 1, 2, 3, 4, oops, and 1, 2, 3, 4. And at the offset of 12 bytes, we copy in the value of EAX, which is now 6. All right. So it looks like whatever the value of I is, it basically adds it to itself. So basically, here I is equals 0, right? Here I is 1, here I is 2, and here I is 3. Right? Do you see how it basically adds it to itself? So a very classical example of the array traversal. So do we have any other questions? Before we go on, I wanted to show you an interesting feature of IDAPro, which can help make your analysis a bit more efficient. For example, let's say I have opened up an executable and I look at the strings window and I see many different interesting strings. For example, the string, which seems to contain the path of the Firefox executable, is indeed quite interesting. I want to know what instructions in the code actually use the string and for what. Well, I can easily find out. So what I'm going to do is I'm going to double click the string. And what just happened was IDAPro has taken me to the read-only data section. I can tell because it says .rdata. That is the section in the PE executable that contains read-only data. And here is the path in question. We can see that IDAPro has given this variable a name. It's right here. So I want to jump to the part of the code where the string is being referenced. So I'm going to right-click on it, and I'm going to select Jump to xref to operand. A window is going to come up, which will list all the instances where the string is being accessed by an instruction. So in this case, it looks like there is only one instance. So what I'm going to do is I'm going to select that instance, and I will click OK. So watch what happened. IDAPro has jumped back into the code, and it is showing me the instruction. You can see my cursor has been put over it, that references the variable in question. So we can see it's a move instruction that copies the address of the string into the parameter space of the remove function. All right? Let's take a look at another example. So I'm going to bring back the strings window. And let's say now I want to find where in the code is this path of the calculator being accessed. Once again, double click. So takes us to the data section where I can see that IDA has named this string with this variable name. So I click on it, right click, and then jump to xref to operand. Again, another window comes up. Looks like there is only a single instance of this instruction. So I click OK. And once again, my cursor has been put right over it right here. Okay, I have accidentally moved it down. So once again, it looks like here is an instruction that copies the address of that string into the parameter space of the remove function. All right. So hope this tip makes your analysis a bit more efficient and maybe just a little bit more fun. All right. Now let's continue with the regular lecture.
Yeah.
Go ahead. Mm-hmm.
This is going to be maybe a bit of a weird one. So we had the if style and the switch table style. Would a compiler ever do something where, say, if you had a large enough possible range of values for the thing being compared, but not a sufficient subset of them are not used, or it's just too large, it couldn't feasibly make a jump table, right? That's I'm trying to think of a way to explain it. It's in my head. Like you have your switch was like comparing I to like 1, 2, 3, but let's say I could be anything between like 1 and a billion, but I only have specific cases for like if I is 557 or something. I don't have a case for every 1 through a billion. I only have a set number of cases, but they could represent values between whatever and a billion. Creating the table would be massive for, let's say, 20 different possible things. Do they ever do something for where could they turn it into like a binary tree sort of logic for the jumps?
I've never seen compilers do something like that, but in theory, compiler could be programmed to do that. Have you folks taken algorithms yet? So if you took algorithms, jump tables are actually sort of an example. Let me come back. In algorithms, you probably covered memoization and dynamic programming, right? So basically, jump tables, they're sort of an application of memoization. So basically, the whole point of memoization is that instead of to save some computation, we end up saving the results of previous computations in an array or a matrix. And then whenever we need to do the same computation again, instead of recomputing, we just look it up in the matrix. Jump tables are sort of like an application of that algorithmic concept, if you know what I mean. And the whole idea behind memoization and dynamic programming is that you sacrifice storage for speed. You do less computations, but you do it at the cost of greater memory, because now both memoization and dynamic programming require you to store the previous computations in memory, right? Like to store the previous results in memory, so you're occupying more memory. So yeah, I mean, I haven't seen compilers, do binary trees and things like that, but in theory, I think it's possible. Compilers are getting more and more clever with, with their approaches to doing things, and so I hope that makes sense. And and if we have billion jumps to make, like we have a condition where I got billion possible scenarios, and I have to take a jump based on that. I mean, it'll be intense, regardless, right? Because it'll be massive amount of comparisons, but also massive amount of memory if I want to jump, if I want to jump table it, if you know what I mean.
Yeah, which is why I was just wondering if it could.
Yeah, and Carl
Okay.
has asked actually an interesting related question. What does it look like if I create a case switch? What is it going to look like in this compiler? And to be honest, I haven't tried, but let's try it right now to satisfy our collective curiosity. So I'm just going to write a very simple program, and maybe I can do something similar, like basically, I can have int I. Can I make it bigger? Maybe not. Or maybe I can. I haven't used this compiler enough to actually figure out how to make it pretty. I think probably compiler options and wire editor options probably. Display size 10. Yeah, let's make it bigger, like maybe 16. Oh yeah, much better. So so I can do, for example, int I, and then I can set it equal to whatever. I wonder if the compiler will basically, see that I hard coded I and will just, just get rid of the entire switch case. But let's see. So switch, and let's do int b equals to like whatever, and then I can do switch I, and then I can do case 1, and maybe I can just do b plus equals 1. Break, and then I can do case 2, and I can do, for example, b plus equals 2. Then I can do case 3, b plus equals 3. Oh, and I forgot the breaks. Don't forget the breaks. And then I can do default. Like I guess like do nothing. And then, or actually for default, let's have it do b just for way of contrast minus equals 1. In which case I'm going to decrement it, and I'm going to do return 0. Let's try to. I just put in desktop. Call it case. Compile. Okay, it compiled. So it should produce an executable called case. All right. So let's go ahead and let's drag it into IDA. Okay. Let's see what we get. All right. And by the way, look at this map. What does it look like? Yeah. So to me, I think I can see already. Can you guess what it is based on this? Is it if style or is it a jump table? Yeah, it definitely looks like an if style, right? So basically, so this is the end of my, stack setup code. So the real stuff begins right here. So it's moving 10 into B. Then it moves 10 into I and 0 into B. So we got something like this going on. So we got I is equal to 10 and B is equal to 0, right? And then I move the value of I into EAX, and then I move EAX into some other variable which was created, probably a variable generated by the compiler internally. So what are we moving into it? We're moving in the value of 10. So, and then we are comparing, we do a CMP of 10 to 2. And if they're equal, then it looks like I jump to right here. So, and in this case, it looks like I'm going to increment it by 1. All right. And if they're not equal, then I check. Is var C greater than 2? So if it's greater than 2, then we go to the next check. If it's less than 2, then we compare it to 1. Okay. So, and if it is equal to 1, then we increment it by 1. And if it's not equal to 1, then basically it looks like we go right here. And then we have a jump to this location where we decrement. Yeah, basically, so if it's if it's less than 1, it looks like this is where we are doing the default, right? That's where we're decrementing. Okay, and yeah, so basically it has constructed. Yeah, this is definitely if style. Yeah, 100%. This is if style, and it might even it may even look a little better if we do this, right? Like if I view it flatly, right? I mean, you can definitely see that we're basically doing CMP, right? So if it's equal to 2, then jump to this address right here, where we incremented by 1, right? And otherwise, if it's greater than 2, then I'm going to jump right here, wherever that is. All right, so, and then in this case, we are comparing it to 3. And if it's equal, then we jump to this address, and it looks like here we are adding 3 to the value of I. Yeah, so definitely classical if style. So this compiler used a classical if style for this one. Make sense?
Yeah, but it also looks like it's doing kind of what I was trying to say, where it's
a little bit, yes.
A little bit where it said like, oh, I'm not just going to compare 4 different times. I'm going to see if it's in this half or this half of my possible. And okay.
Right. Yeah, it's trying to do a little bit of that. Yeah, that's true. Yeah. So it looks like this compiler is smarter than I thought. So I've never tried actually reverse engineering the case here, but yeah, but a definite if style with with some optimizations. Yeah. In G++, you can actually turn optimizations on and off. There is -01, -02. All of those are switches in order to turn different compiler optimizations on and off. So, yeah. Right? Make sense? Yep. All right. So do we have any other questions? All right. Can we see the jump table in IDA? So for that, I would need to have a compiler that would generate a jump table. Yes, I don't know if GCC will do that, but I can try. Let's see. Let's see. Now, of course, GCC is not going to compile that into a PE executable. It'll be an ELF executable, but IDA should be able to reverse engineer ELFs as well. So, All right. Oh, my IDAPro actually, this IDAPro does not support reverse engineering of 64-bit executables, unfortunately. So maybe I can use Godbolt though. Let's see if this will work in Godbolt. I haven't tried it in Jittery yet. Let's see. So I can just choose GCC. All right, and then x86, 64, GCC. Let's see. Yeah, it looks like it is still using some sort of a jump table. Let's see. Let's use another version of GCC. It's actually using 64-bit. I want to use 32-bit. And what does Visual Studio do in that case? Let's see. Yeah, it looks like they're all doing some sort of a if. Yep, still an if. Yep. No, jump tables are real for sure. And also, whenever you write assembly by hand, jump tables are very nifty. I did see them used before. I just didn't know what compiler was used to generate them. ARM 32-bit. Clang x86 64. Oh, it has compiler options. Let's see. Yeah, it looks like all of them are using jumps. I'm sorry, the leaf style. Yeah. What is this F5? Yeah. 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 I don't remember which compilers actually use jump tables for such cases, but yeah, but I did see them used, I swear. And also, when assembly is written by hand, jump tables are used quite often. So why is it preferring if? Probably because one of the reasons is because that's what it was programmed to do. Maybe it's not smart enough to do a jump table, or maybe it's because I just have such a small comparison. So, yeah. All right. All right. So, do we have any other questions? All right. Questions? Mystery 3. Okay. Let's see. Mystery 3. Let me take a look. Where did that go? Let's see. Mystery 3. Where'd it go? Where'd it go? Oh, there it is. And let's see. So mystery 3. So mystery 3. It has to do with structs, and the structs are not on the exam, but yeah. But we could go through it if you want to. Yeah. All right. So yeah, basically structs are somewhat similar to arrays, except in arrays, all of the elements have the same size. Whereas in a struct, it's kind of like a non-uniform array, because like if your struct has a character followed by an integer, followed by, say, a double, right? In memory, it can look like this, because character is typically 1 byte. So you can have the first slot that looks like this. So that's a character, and then you have an integer, which is 4 bytes. So like then you have like the second slot that looks like this, and then you have a double, which could be 8 bytes. So it looks something like this. So whenever you're accessing elements of the struct, it's not just a simple matter of of multiplying your index by the size of a single element, but rather you have to add the size of everything that comes before. All right. So it's like, for example, if I wanted to access the first element of the struct, which is a character, I would just look at the base address of it. If I wanted to access the second element, which is an integer, I would have to do base address plus 1 byte, since the size of the character is 1 byte. If I wanted to access, the double, I would have to do base plus 5, because here we have a character, which is 1 byte, and then here we have an integer before it, which is 4 bytes. So to get to the beginning of the double, I would have to add a 5. If that makes sense? Yeah. So that's basically the idea. Yeah, and we'll talk more about it after the exam. All right? Yeah, but do try the quizzes. Definitely try the quizzes. All right? So do we have any other questions? Questions? Sure. Yep. And as you're studying, feel free to let me know if you have any questions, and we will do another review session on the Saturday. We'll go through basic static and basic dynamic. And like I said, if you want to go through a few more programs, I can definitely put some more together for practice. All right. And the last and the recording where we covered arrays and structs in the last review session, it's going up tonight. The first 2 videos are already posted, and the last video is going up tonight. It's actually rendering. I actually hope it finished. So, all right. So that's basically the idea. If there are no more questions, then I hope you all have a great weekend and good luck in the exam. If any questions, feel free to ask me. And, you can crack any malware, and you can definitely crack this exam. All right? So, as always, peace.